Hello, everyone. Welcome to the third part of this video lecture series on Bayesian deep learning. This video is about posterior inference. Now that we've defined the model, defined priors, now let's consider getting this posterior distribution, the distribution of all the weights given the training data. And the most important thing to note is this posterior is not identifiable. So what do I mean by that? Consider this very simple neural network with two hidden units, H1 and H2, and it computes an output or prediction y hat by the linear combination of those two hidden units. For some given values of the weights, we can find an equivalent neural network simply by switching the weights accordingly. So that is, if we flipped the value of these two weights and then flipped the value of these two weights, we would have a different neural network in that the values would have changed, but y hat would be exactly the same. And so because of that logic, we say neural networks have permutation and variance. In general, for a given hidden layer, if you change or permute the values of the hidden units and you apply a corresponding permutation to the weights, you get the same subsequent hidden units and therefore the same neural network output. And so in the neural network posterior, because of this, we know there'll be equivalent modes where the actual function represented by the neural network is exactly the same, but the weights will be permutations of each other. However, this isn't the only non-identifiability in neural networks. We also have things like scale invariance for ReLUs. That is, if you had a ReLU activation and you multiply the weights in a layer by alpha, some positive scalar alpha, you could multiply the weights in the next layer by 1 divided by alpha, and you'll have the exact same values if you never perform this multiplication in the first place. And so this is a form of scale invariance. And again, this also creates pathologies in the posteriors where you get essentially equivalent networks. And these are just kind of two, but these aren't the only ones. And so because of this, you can see that posterior inference is somewhat ill-defined from the start, right? We probably don't even want to capture all of these equivalent modes per se, because we're simply just wasting computation by getting equivalent solutions. Okay, with that out of the way, let's kind of go through our Bayesian checklist. You might first ask, okay, is there any form of conjugacy we can get? Well, not surprisingly, not in general. But these weights will be buried within kind of layers and layers of nonlinear activation functions, so there won't be any form of conjugacy in general. But if you think about the last layer of a neural network, so say we're just using this neural network for real valued regression, the log likelihood would look something like this, where we have our last hidden units times our last weights. And we can essentially just treat this as a linear model, right? If we assume the hidden units are fixed, this is just then like a linear model, and then this could be conjugate for some choice of priors, such as a normal prior on W here. And so this is a nice little trick in that you have a deep neural network, but you just perform Bayesian inference in the last layer. So people call that a neural linear model. But yeah, in general, you can't really just do you can't rely on conjugacy, especially for weights beyond the last one. And so next you might think of map estimation. And map estimation is where we just optimize optimize to find the mode of the posterior. So we do that just by considering the likelihood in the prior terms. A nice thing about normal priors is that they give a simple ridge penalty. And this, of course, corresponds to weight decay, a common regularization strategy for deep learning. So map estimation is very tractable and does very sensible things for normal priors, say. And so because of this interpretation, you might say, well, we're always kind of doing a form of Bayesian inference if you're using weight decay. But really, map estimation is kind of not true Bayesian inference. We're only learning a point estimate. We're not really integrating out our uncertainty via a predictive distribution like we saw before. And also note that map estimation can have very different characteristics than the true posterior. So here's a nice paper about that I urge you to check out on Bayesian classification with Laplace priors. It shows that if you have a map estimate, Laplace priors correspond to lasso regularization, which is a sparsity-inducing regularization, but the posterior under a Laplace prior is not sparse. And so you get very different kind of character of solutions based on map estimation or not map estimation. Okay, so a second alternative is Markov chain Monte Carlo. And so just to demonstrate this, if you haven't seen it before, imagine we have two weights, W1 and W2, and we have our posterior. Again, this looks like a complicated posterior, but really this would even be simpler than a true neural network posterior. What Markov chain Monte Carlo does, MCMC, is performs a random walk across this posterior, collecting samples along the way. So this means that instead of having a density for the posterior, we run this for a while until the chain is said to converge, and we have a bunch of samples, we'll call them S here, and we approximate the posterior according to these posterior samples. And so we don't get a simple density function at the end of the day. We have a bunch of samples of weights. And so one thing that you can already see is this could be quite costly to store because we essentially have to store S neural networks. But the nice thing about MCMC is that it has theory that it will converge to the true posterior asymptotically. And so it is in some ways considered the gold standard. And so here is some pseudocode for how you run MCMC. You first, and I'll show it just for a scalar weight W. So first you initialize that weight, and you'll run for T steps. You'll first sample a uniform distribution, sample from uniform distribution 0, 1. Then you'll sample a weight from our proposal Q. That is, we take the previous weight, condition on it, and that will sample us a new weight W star. And then we perform the accept reject step. That is, we look at this ratio, which is the posterior joint under the new sample versus the old value, and what's called the correction term for symmetry. And if this value is greater than the uniform sample, then we said to accept the proposal. As we set WT equals W star. If that value, if that equality does not hold, then WT is just set to the previous value. We reject the proposal. Again, with this being the proposal. For neural networks, the hardest part of this procedure is this task right here. We have a very high dimensional space, all these weights. We need a proposal to be efficient in that we always need to be generating kind of interesting and good new weights to help us explore the posterior. But this is hard to do in such a high dimensional space. As this is where something called Hamiltonian Monte Carlo comes in, or HMC. This uses gradient information to improve the proposal generating process. So in its simplest form, as I show here, we have an augmented variable system where we have our usual neural network weights W and this auxiliary variable V. And what happens is we compute the gradient of the posterior. Notice that we don't actually need the posterior here because the marginal likely term will drop out. So this is equivalent to the gradient of the joint distribution between the likelihood and prior. We update our v variable with that. And we take v and update our w variable. And we will run this back and forth several times. And after capital N steps, we will generate a proposal, W star, and plug it into the algorithm we showed before. As you can imagine, this gradient information helps us a lot, right? Because this tells us how to travel around the posterior much more efficiently than just some naive proposal queue. And so this helps us a lot, but as you can imagine, evaluating this kind of multiple times just to generate one proposal is going to be very costly. And so we might need some kind of approximations for that. I'll get to those approximations in a second, but one recent paper of note did try to run as kind of high quality HMC as possible on interestingly large neural networks. And they had to do this on 512 TPUs, so needed Google scale to do it. And they did find posteriors that we'll look at in a bit more, but here just to see a 2D simulation of a posterior, right? We see it's complicated as expected, it has multiple modes, kind of a lot of skew and correlation. And so if kind of HMC in its purest form is too expensive to run, we can run something called Langevin dynamics. And to understand Langevin dynamics, it's really just a simpler form of HMC. So just consider one iteration of the HMC steps, where we get our W1 from W0 plus alpha times V1, and plugging in the value of V1, which is the gradient term plus V0. We see this is essentially equal to gradient updates, right? Because this is our gradient descent equation plus some noise, right? This is drawn from a normal distribution. Right? So it's like a noisy gradient descent where we take our current parameter value, take its derivative of the posterior, and then add some noise to it. This is how you get Langevin dynamics, essentially. Where you take the gradient of the posterior, you add it to your previous parameter estimate, and you also add some noise. And so, of course, this is much, much faster to evaluate because you're going to generate proposals for every step. So I should have made that more explicit in these slides, but this right here can be your W star directly. And so there's multiple versions of Langevin dynamics where you can run adjusted Langevin dynamics where you run actually an accept reject step for every proposal. You can run unadjusted where you always accept the proposal. And so this truly would be like stochastic or noisy gradient descent, where you just do gradient descent, but add this additional noise term B. And you can make this faster still by subsampling data to compute this gradient. So that would give you two forms of stochasticity, one for the mini batch noise and one for this extra noise term that drives the Langevin process. And so this represents a smooth continuum, not so smooth, but a continuum between HMC and Langevin dynamics, where HMC is kind of the gold standard. If we run of these for less iterations, we start to get something closer to Langevin dynamics, and we can even then start throwing away the accept reject step and the stochastic gradients. But of course, all of these kind of compromises will incur approximation costs. There's also theory that even says once we start using stochastic gradients and mini batching, we're already kind of guaranteed to never recover the true posterior. The paper I mentioned before from Google and NYU that did the in-depth investigation of HMC for neural networks, they provided this table that compares the accuracy on CFAR10 versus the agreement across posterior samples. And here they include HMC versus itself as a reference. That is, the HMC samples get 89% accuracy on CFAR10. And also they have a 94% agreement in their predictive distribution across the different chains. And we can compare this to stochastic gradient MCMC methods. So we have stochastic gradient longevity dynamics, which is longevity dynamics using mini batching. So it's the kind of most approximate form of MCMC. And also things in between, like stochastic gradient HMC with secular learning rates. And we see that SGHMC with secular learning rates did best. It has actually a comparable accuracy and only a 2% drop in agreement. Longevity dynamics actually does well in terms of accuracy, but it loses further in terms of agreement. Okay, so if MCMC is not an option, we can instead turn to variational inference. And variational inference, instead of doing sampling, is an optimization-based procedure. That is, we take our posterior and try to approximate with another distribution Q, which will have some parameters phi, and we'll try to learn these parameters phi so Q becomes as close to the posterior as possible. So here's just a simple example. If purple is the true posterior, we might have a posterior approximation in green here that tries to fit it as close as possible, but it won't be perfect because we picked a restricted family that can never kind of get perfectly close to the true posterior. And so for these variational approximations, we usually need to assume some degree of factorization. So that is, for neural networks, we can assume they factorize over layers. That is, instead of having a joint distribution over all the weights, we have a product of distributions per layer. Or we could even do something more extreme and assume it factorizes over the weights. That is, we have a Q distribution for every single weight, and this is called the mean field assumption, that there's no dependencies in the posterior approximation. This is, of course, the most efficient and fastest to optimize, but of course, we're losing a lot. We now can't even capture posterior correlations with the mean field assumption. So for normals, for instance, this is again a very common posterior approximation. We would have multivariate normals on the layers, but also just univariate normals on the weights. Okay, so now that we've defined some potential approximations, we can enter the optimization objective. And so the optimization objective for variational inference is to define some divergence D between the variational posterior and the true posterior, and optimize it with respect to the variational parameter C, and minimize it in particular. So a very common choice of divergence is the KL divergence. That can be written as follows, where it's an expectation essentially over Q of the log ratio between Q and P. Some simple algebra shows that this KL divergence can be written as this equation, where we have the negative log likelihood with an expectation over the Q distribution, plus the KL divergence between the posterior approximation and the prior, plus a constant that will go away when we take derivatives. So we don't need to worry about it, but it involves the marginal likelihood. And so now we want to optimize this with respect to the parameters phi here and here. And in general, this equation is called the evidence lower bound, or elbow for short. In computing these two terms, this term is fairly easy because it is the KL divergence between our prior, which is again something fairly tractable, like a normal, and maybe even a normal posterior approximation. So that KL divergence would be found in closed form, or even if this is not in closed form, it can be estimated fairly well by Monte Carlo sampling because it doesn't involve the deep neural network. Right? The deep neural network is involved here, and so we have to have the expectation over variables that are buried deep within the neural network, and so that's why this term is pretty hard to compute. And so the main trick for evaluating this term is what you might have seen already for variational autoencoders. It's called the reparameterization trick. That is, we take this expectation over our variational distribution Q and reparameterize it as another expectation over some alternative distribution. We'll just call it eta here for the random variable. And we'll define the weights to be some function of eta. And that function will take in our variational parameters, and that's how we'll get the equivalence. I'll show a concrete example of this function in a second. But once we have this reparameterization done, we can then simply do Monte Carlo sampling to approximate the integral. And this is an unbiased sample. And so now when we want to optimize the neural network, we can then take derivatives of this expectation simply by doing the reparameterization and pushing these values through the Monte Carlo expectation. And again, and we have direct access to these variables because we've written them in terms of G and separated the stochasticity by using this auxiliary distribution eta, or auxiliary random variable eta. So the general technique is called Bayes by backprop, and it was introduced in 2015. And so for particular examples, so say if our Q distribution is normal, we can use the normal's location scale form to define this G function. And so G here would be the normal mean plus its standard deviation times eta, where eta is drawn from normal 0, 1. And so this transformation makes eta equivalent to this Q here. And so we would write this exact equation in the neural network. That is our hidden unit times our weights. Hidden unit times our weights would simply be our hidden units times mu plus sigma times the noise variable eta. Right? And that's how you would implement it in your code. And well, you would take backprop with respect to mu and sigma. For a general Q, you can always use the inverse transform. So that is, if you have access to the inverse CDF of Q, you can always sample eta as a uniform distribution and put that sample back through the inverse CDF. This is called inverse transform sampling. The only hang-up is that you might not have access to this inverse CDF in a nice analytical form. So now I'll return to that table I showed before, comparing the stochastic gradient MCMC methods with HMC. And now I'll add to the, or show in that table, the mean field variational inference column. And we see that using mean field variational inference results in a drop in accuracy from 89% to 86%, and also less agreement between the mean field samples and the HMC samples, dropping from to 88%. And so again, we see a clear degradation between the MCMC and the VI. Although, maybe this is actually surprisingly good, right? Like for such a strong assumption, you might expect the results to be even worse. Okay, for the last approximate inference method I'll talk about is another variational inference technique called the Laplace approximation. And so here we'll try to approximate, again, the posterior, just writing in terms of one weight, as a particular normal distribution, where the mean of the normal is determined by the map estimate of the weights, and the covariance matrix is the inverse of the Hessian matrix evaluated at the map estimate. In particular, this Hessian matrix is the matrix of second derivatives of the log joint. Oh, sorry, this should be just this, no inverse yet. So why is this a good thing to do? So you can imagine as follows. We run some sort of stochastic optimization, like stochastic gradient descent, to find a point estimate as the map. And then once we're there, we compute that Hessian matrix. And that gives us a covariance matrix that is formed by the local curvature in that kind of local minima that we landed in with the map estimate. And that is our posterior approximation. And so a really nice thing about the Laplace approximation is that you can actually apply it to any pre-trained model that you might find online. So for instance, you find some model, you already have its weights, point estimated. You can just assume those parameters are the map, even though kind of we're technically violating the true spirit of Bayesian inference here by just kind of assuming they're the map or assuming there's some good mode. And then we simply take the compute the Hessian around those parameters and say that's our Laplace approximation, and we had to do essentially no training. It was just a second step that we applied to a pre-trained model. The big con with the Laplace approximation is the Hessian matrix can be numerically unstable, and we often need to assume some sort of structure to make it tractable, right? So the Hessian matrix in general, we'd be inverting a matrix that's number of parameters by number of parameters, which is just way too big. So we need to assume kind of low rank or block structure, and sometimes we even need to assume it's a diagonal matrix. Right, so essentially making kind of a mean field assumption within the Laplace approximation. Okay, so now I've covered the primary techniques for obtaining the posterior for neural networks. Conjugacy is available at times for the last layer, and so that might be a viable option for you, and one that is kind of less computational overhead than other methods. If you care about getting something fairly close to the true posterior, MCMC is an option, but it will usually require approximations and some careful computational implementations. And variational inference is practical for much larger neural networks, but as is not too surprising, given that we have to assume some restricted form, we'll often run into inferior performance compared to MCMC.